So, according to Langevin theory, which was an attempt to, which is a successful attempt to improve on the Einstein's theory, um, the average force acting on a suspended particle, which is the Brownian particle, um, due to molecular bombardment, is made up of two components. It has a frictional component and a fluctuating component. Okay, so he definitely accepts the basic premise that the Brownian motion is because of the of the of the bombardment of the surrounding liquid particles and the liquid molecules with the Brownian particle, and the force due to the force acting on the suspended particle. Let me write it down for you. Force acting on the suspended particle due to molecular bombardment is made up of two components. One is the frictional component, and another is a fluctuating component. Okay, so that was the assumption. So which can be expressed as, so this frictional component is the and then which I will tell in a short while. Basically, the frictional component, it is a microscopic contribution, and fluctuating force is a macroscopic contribution. Okay, and the fluctuating force is due to the molecular bombardment, whereas the frictional component is because of the viscosity of the liquid. So you have this this particle confined in the liquid, right? So naturally, one can always think that there is a viscosity for this water or the liquid in which it is placed. So there is a contribution which will have an effect on the suspended particles movement from the viscosity of the liquid. So that makes the frictional component, and then the fluctuating component, which is because of the molecular bombardment. Molecules means the water molecules, for example, the liquid molecules. The liquid molecules do bombard, and that makes the fluctuating component. So in this Langevin theory, this contribution is written as mx double dot, which is ma, right? Mx double dot. The force is equal to F plus Fx, where F is the frictional one and Fx is the x component of the fluctuating force due to molecular bombardment. So let me remind you one of the assumptions in which Einstein um, himself accepted the mistake which he did, which the Langevin theory is correcting, which is about the inertial part of this. So he missed the Einstein missed making the mass of the suspended particle or the Brownian particle as a component of this equation, whereas in Langevin theory he puts that into his first and foremost expression itself. So this is the what M stands for the inertial, the inertial component in a way. So let's say, so mx double dot is equal to f plus fx. So if I take the equation of Einstein as equation number 1, this will be equation number 2. So if I take the f part, substitute and separate. So in his calculation of the frictional component, Langevin assumes that the suspended particles are spherical in shape, and therefore it can be expressed in terms of the viscosity of the solution, of which the expression is F is equal to minus 6 pi eta r x dot, where eta is the coefficient of viscosity, r is the radius of the suspended particle, and x is the so-called displacement. So here we are taking x dot. So if I take this as c, then I can write down F is equal to minus c cx dot. So c is equal to minus 6 pi eta r. So therefore I can write mx double dot is equal to cx dot plus fx. So what can be the comment about the so-called fx, f of x, right? So this f of x by definition itself is totally fluctuating, and one of the major characteristics or the observation on the Brownian particle is that they move randomly, but over a long time. This randomness means that they move in all directions equally. So the displacement will be 0 over a long time. So this is one of the central part of the observation which we make. So therefore, both Einstein and Langevin does not calculate the x, but instead they calculated the mean square displacement, so that because x will turn out to be 0. So, but instead they calculate the mean square displacement. So therefore, we will, in order to do that, we will make a correction by multiplying with x in the equation number 2, and then we can write that expression as mx x dot double dot, of course, is equal to minus cx into x dot plus x fx. So this is equation 4, this is equation 5. But we know that d by dt of x squared is what? Is equal to 2x into x dot. And Therefore d by dt squared of x squared is equal to 2x into x dot plus 2x dot squared. We can substitute, say if I take this as equation 6, we can substitute this equation 6 into equation 5. So we are substituting equation 6 into equation 5. Then I will get m by 2 d squared by dt squared x squared minus m x double dot squared is equal to minus c by 2 d by dt of x squared plus x fx. So this equation is valid for one of this particle. So this is the expression, and this equation is valid for one single, if we track the motion of one single particle. And if we take lot of particles, many particles together, and in that case we can modify this expression by putting an average into this expression. So when we consider many particles and we take the average, then I can write the above expression as m by 2 d squared by dt squared x squared average minus m x double dot did I missed anything? Yeah, x double dot squared is equal to minus c by 2, of course the average is there, minus c by 2 d by dt x squared plus x fx average, right? So here in this expression, this x and fx are quantities which vary rapidly. So this term will become 0. Again, I know that I did a mistake probably. This should be mx dot. I think so. So the mx dot squared. So I can always do the substitution that I know that for a typical system in thermal equilibrium of this fluid molecules, their kinetic energy is equal to half kBT. Right, half kT in each degree of freedom. Since we are taking only the x direction, we are taking only one single direction. So the kinetic energy will be half kT. That means half mv squared is equal to half kT. So therefore m x dot squared is equal to kT. Is equal to kT. So therefore I can substitute that, and then after those substitutions I will reach the expression I will modify that above expression as m by 2 d squared by dt squared x squared plus c by 2 d by dt of x squared is equal to kt, which I can modify and write it as d squared by dt squared x squared average plus omega d by dt of x squared average is equal to 2 kt by m, where omega is equal to c by m, and you know what is the c means by, right? C is equal to 6 by eta r. Actually, I should be putting a minus here. So c is equal to 6 by eta r. So omega is equal to c by m. Now, in order to solve this equation, we assume that averaging over space and differentiation with respect to time are commutative. Our reasoning is quite, or Langevin's reasoning is quite significant. So you can think it like this. There is one of the ways to think about is that it is equivalent to take averaging for n particles to taking, so if I have a system of n particles and I track the movement of those particles for of all those particles for a time interval, for one single time interval, it is equivalent to do that. I track down n number of particles, capital N number of particles for, sorry, let me repeat. So in the first experiment, I take n particles and I track it for a particular time. That's one way of doing it. It is equivalent to assume that I take one particle and I track that one particle for n interval of time. Here I was tracking it for one interval of time. Here I take one particle and I track it for n interval of time. But the second experiment is more efficient because I need to concentrate only on one single particle. So therefore, his reasoning that averaging over the space and differentiation with respect to time are commutative is quite physically admissible in this expression. So he does that, and therefore I can write d squared by dt squared is equal to d by dt of x squared. Right? This is what we just now wrote. Now let's imagine that d by dt of x squared average, I call it as a u. So therefore I can now write down that this expression as u dot plus omega u is equal to 2 kt by m. Okay, so this is the expression which Langevin basically came up with. Here in this expression, you have the m also being taken into consideration. You have the omega. Omega is the c by m again, right? Which is also taken into consideration. And this equation you can solve it. U dot plus omega u is equal to 2 kt by. It can be solved as u is equal to 2 kt by c plus a exponential minus omega t, where t is the time. So this is Langevin's theory. And this equation does take care of the inertial component and the frictional component together. And also it takes into consideration the fluctuating force, which is because of the collisions. Now, as I told you, the Einstein's theory is a limitation basically, right? So which is quite demonstrable, which can be quite demonstrated from Langevin's theory. So basically Einstein's theory is a subset of the Langevin's theory, which I can demonstrate it now here. Say if I take a new case. So in that expression, so if we neglect m, what will happen? Neglect m means I have the omega is equal to c by m, right? Small m means large omega. Okay, small m means large omega, and therefore large omega means this exponential term over here will become very small. So what happens is my u is equal to 2 kt by c, right? Because I can neglect this second exponential term because the omega is now very small, because omega is very large, and therefore it is minus exponential raised to minus. So since omega is large means I can neglect that. So neglect m means large omega. So I can write u is equal to 2 kt by c. So if we integrate now imagine that I integrate now this expression from t is equal to 0 to t is equal to tau. Tau is the time in which I do this whole experiment, right? So integral 0 to tau dy dt of x squared dt is equal to 2 kt by c integral 0 to tau dt. So if I carry out this integration, I can write x tau squared minus x 0 squared is equal to delta. If I take this as delta of x squared is equal to 2 kt by c into tau. Therefore delta x squared is equal to 2 kt by c into tau, which is equal to kt by 3 pi eta r into tau, which is, if you compare this expression with our original expression for the Einstein's theory, they are the same thing, right? So the equation number 1 and this expression are absolutely same. So Langevin theory gives the flexibility for accounting the special case where the Einstein's theory is valid, in which he neglected the inertia component. So that is the beauty of this Langevin's theorem. So it is generally described as it happens at a particular time, because since Einstein was more concentrating into the diffusive regime, its time will be really large, whereas he totally neglected the kind of vibration which this kind of the particles, which the random motion which these particles make at very short instance of time, which was in turn related to the mass of the inertia of the movement of the suspended particles. Okay, so we will discuss further on this in our live class. Okay, so that's for now. So the takeaway is that we define what is a Brownian motion means by, and we know what is the Einstein theory, how he computed this expression, the assumptions on which he computed this expression, and we also know the limitation or the mistake which happened in the Langevin theory. In the Einstein's theory. Then we went on to discuss the Langevin theory. The Langevin theory, we first of all wrote the expression, the basic expression which consists of the inertial component, the frictional component, and the fluctuating component together. We wrote the expression for that, and then finally we reached into an expression which represents which is equal to u is equal to 2 kt by c plus a exponential minus omega t, which is the Langevin theory. And this t over here, this capital T is temperature, whereas the small t is the time. So the small t over here takes care of the time interval in which we need to calculate this kind of a trajectory calculation. In the theory of Einstein, he was having a time tau. The tau was the diffusive process time, which is a constant time interval. Whereas in the Langevin theory, he puts a t as one of the variables. So therefore, I can very precisely go through this real trajectory and get the correct trajectory in the Langevin's theory. And we also demonstrated that the Einstein's theory can be derived from the Langevin's theory, just assuming that the inertial mass is totally small, or it is viable to be neglected. So therefore, in that case, we can derive the Einstein's theory from the Langevin's theory. So that's what. Okay.